Canary Wharf Station is a structure built on the water which made dewatering an essential part of the construction process. At the same time, the fact that part of the structure extends below ground level is another key aspect to consider when discussing construction methods. This is exactly why the top-down construction method was necessary for this project. In previous videos, we looked at cover dams and top-down method. In this session, we'll take a deeper look at how this method were specifically applied on our site. A cover dam is temporary watertight structure installed in underwater construction to block water and create a dry work environment. Typically, cover dams are used for small-scale underwater projects like bridge foundations or pumping stations. They are usually dismantled after short-term use, so the design prioritizes cost efficiency over structural stability. However, the cover dam used at Canary Wharf Station was highly unique. The station itself had to be constructed inside the cover dam, making it a large-scale and long-term installation. Moreover, unlike typical cover dams that merely block water, some of the piles here were designed to serve as permanent structural elements. This required a fundamentally different design approach and functionality compared to conventional cover dams. The construction began with the installation of tubular piles. Starting from the center of north wall, a total of 310 piles with an outer diameter of 1.2 meters, a length of 18 meters, and a wall thickness of approximately 14 millimeters were used to form the cover dam on the east, north, and west sides. Considering the characteristics of the site, tubular piles were selected for this project. These piles were pressed into the ground using the silent piler from Giken, a Japanese company. Unlike conventional methods that use hammering or vibration to drive piles into the ground, the Canary Wharf Station project adopted a hydraulic pressing method that quietly pushes the piles into the soil without impact or vibration, as it was located in a central urban area. Before pressing the piles, an auguring method was used to pre-bore the ground, followed by hydraulic pressing to install the piles. In addition, due to the importance of water tightness in this project, interlocks were used to connect the piles and prevent water from entering the cover dam. Furthermore, to reinforce the water tightness of interlock joints, geotextile, a waterproof treated synthetic fiber sheet, was inserted, and cementitious waterproof grout was injected into the gaps to complete a watertight cover dam. In this project, the structure had to endure loads over a long period and serve as a permanent structure. Therefore, additional reinforced concrete piles were installed inside each steel pipe pile to provide internal reinforcement. After driving the steel pipe piles to a depth of 18 meters, a dry bore hole was created inside each one, and then RC infill piles were inserted down to a depth of 63 meters below the water level. However, internal reinforcement alone was not sufficient to resist external lateral loads and hydrostatic pressure. Therefore, after the installation of the steel pipe piles, additional anchor piles were constructed outside the cover dam to support it. Once installed, these anchor piles were connected to the cover dam steel pipe piles using tie rods. This system was essential to prevent the cover dam piles from tilting or deforming during construction. These anchor piles have the same specifications as the main cover dam steel pipe piles: an outer diameter of 1.2 meter, a length of 18 meters, and a wall thickness of approximately 14 millimeters. However, there was a key difference in the depth to which the internal RC piles were installed. Since the steel pipe piles were part of the permanent structure and needed to stably support the construction of sublevel 6, which lies about 25 meters below the water surface, the RC infill piles were installed to a depth of 36 meters below water level. In contrast, the anchor piles were designed as temporary structures to be removed after construction. Hence, installing deep RC piles inside them would be an inefficient design choice. After constructing the cofferdam, the water within the site was pumped out, creating a dry working environment. Following this dewatering process, the southern wall of the station was installed, along with the plunge columns. On the southern side of the site, existing building foundations made it impossible to install ankles and tie rods externally. Therefore, the design required securing structural stability by relying solely on the internal rigidity of the second piled wall system to support the ground. The second piled wall is simply put, a dense and interlocked wall formed by drilling and casting large concrete columns in an overlapping pattern. It is a continuous wall structure that prevents soil collapse and groundwater inflow. This system begins with the installation of soft piles made of unreinforced concrete, which act as the initial earth retaining structure. Between these, hard piles made of reinforcement concrete are inserted to secure the required structural strength. With this, the full construction of the cofferdam was completed. Now, it was time for top-down construction method. At the Canary Wharf station site, the conventional bottom-up method, which involves deep excavation followed by the construction of upper structures, was not feasible. This was due to several factors. The site was surrounded by a complex network of underground infrastructure, including multiple railway tunnels and utility cables, and densely packed high-rise buildings. Conducting deep excavation all at once posed a high risk of damaging these surrounding structures and made it difficult to safely withstand the earth and water pressure. Therefore, the top-down method, which allows for simultaneous construction of the upper and the lower structures by casting each floor slab and excavating underneath it layer by layer, was essential for this project. The top-down construction process consists of installing plunge columns, constructing slabs, repeating excavation beneath the slabs and slab construction for each floor, and finally excavating the lowest level and constructing the base slab. First, there are the plunge columns, which temporarily support the load of the main upper slab during the top-down construction. Due to the nature of the top-down method, installing slabs from the top down while excavating below, immediate support is required during this process, and the plunge columns play a crucial role in providing that support. A total of 30 plunge columns were installed on site, driven 14 meters deep along the center line, deeper than the floor level. Plunge columns are typically installed where reinforcement concrete columns will later be placed. Once excavation is complete and the permanent columns are installed, the structural role is transferred to those permanent columns. Integrated with the upper structure, the plunge columns serve as permanent structural elements. Next is the slab construction phase. The first level to be constructed was the third basement level, or sublevel 3, which is the closest to the dock floor after water drainage. While the slab construction on sublevel 3 was underway, excavation and foundation work were simultaneously progressing on the lower levels. At Canary Wharf Station, construction was carried out concurrently on sublevel 3, 4, and 6. It is important to note that sublevel 6 was constructed before sublevel 5. Canary Wharf Station was a place through which the TBM had to pass for the line construction. Therefore, space had to be secured for it to pass. The subway runs at the lowest level of the station, sublevel 6, so the TBM also had to pass through sublevel 6. The diameter of the TBM used in the Crossrail project was 7.1 meters. If sublevel 5 was constructed first, the TBM would either have to break through that level while passing or might not be able to enter at all. Therefore, instead of building sublevel 5 first, sublevel 6 was constructed to secure space for the TBM. In fact, the floor-to-floor height difference between the sublevel 4 slab and sublevel 6 slab is 10.1 meters, and by removing sublevel 5 in between, a vertical clearance sufficient for the 7-meter TBM to pass was secured. The TBM was originally scheduled to arrive in the second half of 2012, so excavation down to sublevel 6 was completed by July 2011, and preparations to receive the TBM were finished by March 2012. By that time, construction of sublevel 2 and sublevel 1 had already been completed. However, due to unexpectedly harder ground conditions than designed, the TBM that started in May 2012 was delayed by about 7 to 8 months and finally reached Canary Wharf Station on May 31, 2013. Only after the TBM had passed was sublevel 5, the platform where passengers actually board and alight, constructed. However, having the TBM pass directly through the station was a significant structural challenge. The TBM generates strong vibrations and horizontal loads on the ground as it moved through. At this time, the top-down slabs played a crucial role in supporting the ground in the section where the TBM passed. In addition to supporting the structure, they also helped reinforce the ground itself. This week, we focused on the structural construction of the station prior to the main internal building works, with particular emphasis on the cofferdam and top-down construction methods. Next week, in week 10, we'll cover topics such as ventilation, the rooftop garden, and roof structure, as well as the materials used for the roof. In week 11, we plan to conclude this series of the presentations by providing a comprehensive overview of Canary Wharf and telling the overall story of the selected building.